All right, welcome back, students. Again, we're continuing looking at this trigonal planar example of boron hydride, boron trihydride, however you want to, I don't actually know the proper way. I probably do it somewhere in my brain, but I don't know it today. But we'll call it boron hydride as our example for thinking about sp2 hybridized orbitals. And in this video, we're going to be looking at the actual energy diagram and what those molecular orbitals look like visually. So again, we'll build up our energy diagram for boron. The 1s is significantly below the 2s, so there's a break in the energy axis. And then you'll see that here the 3 hydrogen 1s orbitals are actually a little bit higher in energy, just barely, than the 2p on boron. And so we have our 2s, our 2p for boron, we have our 1s's, one for each of our hydrogens. They're all drawn next to each other because they are degenerate. They're just spatially in different places. So what does our energy diagram for BH3 look like? So very similar to what we saw with beryllium hydride, this 1s orbital that's on the boron is way too low in energy. It's a core pair of electrons, and so they are not going to be able to contribute to molecular orbital formation or bonding. So they're going to form a non-bonding 1s orbital. If we draw that, we're literally just going to see, right, that circle around the boron. So it's going to be a psi 1s on boron. And we'll see that that remains there. And so as we go further up, we need to form 3 bonding orbitals using our sp2. So 1 part s, 2 parts p. And those are going to drop in energy to form bonding orbitals with our 1s atomic orbitals on each of the hydrogens. And then we'll have 3 that go up in energy, formed from the sp2 and the hydrogen 1s, to form our anti-bonding orbitals, which is going to leave us 1p that's going to stay unused on boron. So let's look at what those look like. So starting at the lowest energy molecular orbital that we form, the bonding one, looks something like this, where we've got the boron and all 3 hydrogens, and we've got this sort of like blob of goo that sort of surrounds the whole molecule, and it's all one direction. If we look at each one of those individual bonds, we'll see that around each bond, this wave function is cylindrically symmetric. I will warn you that that becomes much, much harder to see as soon as we start getting away from linear molecules. So if that's hard for you to see, that's normal. I struggle with that as well. This is even because if we look at, again, each individual bond, so let's just pick one individual bond. In the x direction, y direction, it's got to be even because we're saying this is cylindrically symmetric around the bond, but also along that bond, just between the 2 atoms, it is also along that z direction will be, or the bond dimension will also be even. And so this is going to be a sigma Gerada. And again, it is a bonding orbital. We can draw our next one. So this is 1 up in energy. This should still be a bonding orbital. This one looks a little funky. So this is cylindrical about each bond. Notice that it doesn't even cover one of the bonds, which really is only about 2 of the boron hydride bonds. That's fine. Some of these get a little funky. And now we have a node. Our node here, much like before, as we go up in energy, we should add a node. That node is going to cut through the boron atom. And because of the symmetry for trigonal planar, it's also going to cut through one of the hydrogens. But it's going to leave the other 2 as bonding. So this we can think about as 2/3 bonding. And so we will call it bonding because majority wins. It's cylindrical about each of the BH bonds. But if we think about the XYZ direction, we do have a change in sign from red to blue. We do have a node, which is one of the indicators that we should be an odd function. This is really hard to see, the even and odd here. But this one will be odd, so this is a sigma Ungerada. If we go up one more energy level, we should add another node. That's not going to be very apparent here. Again, we're in weird 3-dimensional space, so technically this has more than one node. But drawing them gets funky. So again, we have a sigma in that if we look at the hydrogen pointed up or either of the hydrogens pointed down, those bonds are completely encompassed by wave function. There's no nodal plane along a bond or encompassing a bond. And so this still is sigma type, which we would expect because we shouldn't have any pi bonds in BH3. And so we have this sigma. This is also going to be an odd function because, again, you have that change in sign. Unless we have multiple changes back in sign, it's usually going to be odd. So this is going to be a sigma ungerata. Again, very hard to see with these. When we go to the next one in energy, now all of a sudden we're back to our unused 2p orbitals. This is a non-bonding orbital. It's centered on boron. It stays atomic. It's not molecular. We go up in energy one more time. Now we should be getting to the anti-bonding because we're higher in energy. This one looks super funky. I don't expect you to be able to predict these, right? Like for this one, this sigma ungerata anti-bonding orbital, I actually had to look it up on WebMO because I don't have this one memorized. But you get this really funky shape. Yeah, really funky shape. It's still sigma in that if we look at any of the bonds, technically there's cylindrical symmetry. This becomes really hard to see because this is now anti-bonding. So there is a perpendicular node along each bond breaking the bond. If we go up one more in energy, we're going to get this very strange looking thing as well. So actually in the up-down directions, that hydrogen that's going up, we called that bond 1 earlier when we were doing the math. That one is actually pi type, and the other two are sigma type. But it's 2/3 sigma type and 2/3 antibonding, so we call it a sigma antibond because majority wins in molecular orbital theory. This one is going to be ungerata because there's opposing sign or opposing color across the boron. And if we go up to our last one, we get this sort of picture where we have a circle or a lobe of blue on the boron and a lobe of red on each of the hydrogens. So we can certainly tell that this one is fully anti-bonding. It's a sigma gerata in that there's symmetry going in all three directions from the boron. And so it does become a gerata function, and that's really, again, really, really hard to see in that this definition of even and odd gets really funky in 3 dimensions. So again, I don't expect you to be able to tell me for anything bigger than a linear molecule, gerata or ungerata. We don't have the time or the amount of in-person time specifically to go over that and to really dive deeply into that. And this is really, really challenging. It's something I struggle with when I don't think about it for 6 months. So I don't expect you to pick it up immediately. But I did want to show you what these orbitals look like. So this is what sp2 orbitals for boron trihydride would look like. We will not be going over tetrahedral or anything beyond tetrahedral. Your book has a very nice example of tetrahedral. They do stop at tetrahedral. Oftentimes in class, I'll go up to sp3d with some of the trig, just because it is kind of a nice, an interesting thing. You do get some fun looking orbitals at that point. But we won't be doing that here. If you are interested in looking at those, I'm happy to share with you some WebMO calculations that I've used in class in the past. Just let me know. With the carbon, the tetrahedral one is an interesting one to know. If you're interested, again, the book does a really, really nice job of walking through tetrahedral.